In this video, we're talking about the dissolution energy of a single hydrogen chloride molecule. And so it takes about 4.5 electron volts to break this molecule apart. Now, given that energy, we want to find the minimum frequency or maximum wavelength of a photon that can do this. So a photon that has exactly 4.5 eV of energy is barely energetic enough to get this done. Any photon with a higher energy than that is going to break apart the molecule and give some extra energy to the two atoms as they fly apart. So let's go after the wavelength of this 4.5 eV photon. And what I'm going to do here is write E equals hf, our classic formula for the energy of a photon. But I can use the speed and frequency and wavelength relation using a wave speed of c, or the speed of light, to replace the frequency with c over lambda. And this one is worth remembering because we use it so much when we're talking about quantum and atomic in this class. Hc, if you put it in the correct units, turns out to be about 1240 eV nanometers. Well, this is really convenient given how often we're working with wavelengths in nanometers. So if I take this equation and solve for lambda in general, lambda is going to be Hc over E for the photon. And then I replace Hc with approximately 1240 eV nanometers and divide by the energy of the photon in electron volts. And I've got an answer popping out in nanometers. To 3 sig figs, I get 276 nanometers. So this is an ultraviolet photon. Remember, the shortest wavelength of visible light is something like a 400 nanometer violet. This is shorter than that, so it's more energetic than that. We call it an ultraviolet wavelength. We were also asked for the frequency here, so we'll go back to this wave speed and frequency and wavelength equation. And solving for frequency real quick, I get c over lambda. And we'll take the speed of light as 3 times 10 to the 8th meters per second. And our wavelength in the correct units would be 276 times 10 to the negative 9 meters. I'm left with units of inverse seconds, which are hertz. And keeping 3 sig figs, I get 1.09 times 10 to the 15 hertz. And again, this is a minimum frequency to break this molecule. Any photon with a higher frequency will have more energy in it, so it'll break the molecule and give some extra kinetic energy to the components. Now, as kind of a footnote on this video, let's look at that claim that Hc is 1240 eV nanometers. In SI units, there's Hc, and I can see that my seconds cancel, and I have joule meters. So all I have to do now is convert the joules to EV, and then convert the meters to nanometers. And there's 1 meter for every 10 to the 9 nanometers. And we smash all the numbers into a calculator. And just keeping one extra digit of precision here, I get 1242 eV nanometers. But generally, when you see me use this in a problem, I'm going to quote it as 1240 because it's close enough for us. If you find the physics content on Zach's Lab helpful, click on the Zach's Lab logo on the right to browse playlists and subscribe to the channel. I produce over 100 new videos per month, and subscribing is the easiest way to find new content. Thanks for watching.